Welcome to Higher Structures seminar series. This week, our speaker is Volker Stern from Bilkent University, and we thank Volker for giving a seminar talk in our seminar series. His talk is that's titled Commutative and Frobenius Algebras in Span Categories. Please, Volker.
Thank you very much for the kind introduction and for inviting me to give this talk. I'm very excited to be speaking to you all. So, as you've heard, I'm going to be telling you about commutative and Frobenius algebras in span categories. And this is, in some sense, the story of one of the threads that has run through my research, starting from my PhD thesis and continuing to the present day, which is these algebraic structures in span categories and how they relate to topological field theories. Now, most of what I'm going to talk about today is the algebraic structures themselves rather than anything on the TQFT side of things. But it is worth keeping in mind that that is one potential motivation for some of what we're going to talk about. I should also say I'm hoping to keep this as accessible as possible. If anything is unclear, please feel free to interrupt me. So to start out with, I said I'm going to be talking about algebraic structures in higher categories or categories of spans. And the first thing that I then need to do is tell you what on earth I mean by a higher category of spans. So the starting data is going to be C, a category with pullbacks and a terminal object, which I have failed to write here, but that's fine. Pullbacks and a terminal object. And from these starting data, we're going to construct a new category. So such categories include sets, topological spaces, vector spaces, and in the higher categorical realm, they might include the infinity category of spaces or the infinity category of infinity categories. So there are many, many examples, and a lot of the most natural examples or the categories that show up very often will satisfy these very mild conditions. And from this category, we can form, beg pardon? I'm sorry. From these data, we can form a category span C. So the objects of span C are just going to be X, Y, and Z, which are objects in the original category. So we have the same set of objects. And then a morphism, say from X to Y, or from Y to Z, is going to be what's called a span. So a morphism from X to Y might be a span G, which is an object in C and two morphisms in C, which I'm in this case labeling suggestively as S sub G and T sub G for source and target, because I'm always going to be reading my spans from left to right. And I'm sorry. And a morphism from Y to Z is going to be an object F and morphisms F sub F, S sub F, and T sub F. And then, in addition to telling you what the objects and morphisms are, I need to tell you how we compose them. And this is where we get into those conditions that I mentioned before, pullbacks. So the composition is taken by forming the pullback. And so we take the pullback F crossover Y with G. And if you like, you can think of this all as living in the category of sets rather than in some arbitrary C, in which case this is just the fiber product that we know and love. And then the two legs of the span are the composite morphisms that go from F cross G over Y to X and F cross G over Y to Z. So this is all well and good. This seems nice. However, I've already lied to you all a little bit in that this isn't actually a category. And the reason for this, in a nutshell, is that uh, this fiber product, this pullback, is only unique up to unique isomorphism, not strictly unique. And so even if we choose, for instance, a representative for every possible composite, so fix a choice of pullback, there's no reason to think that that will be strictly associative. And so what we need to do instead is add a little bit of higher categorical structure. So we have this problem that pullbacks are not unique. And the way we solve this problem is to build a bicategory instead of a category. So this will solve our problem because then we don't actually require strict associativity of composition, but rather associativity up to canonical 2-isomorphism, which is precisely what this uniqueness up to unique isomorphism will give us. So if we're now forming a bicategory, I still have to tell you what the 2-morphisms are. So let's suppose we have a diagram where we have a morphism F and a morphism G from X to Y. Oh no, there's an error on the slide, so let me annotate. A 2-morphism is going to be a morphism in C from F to G that makes both of these triangles commute. So this will be our appropriate notion of 2-morphism. And it's worth pointing out here that everything that I'm going to talk about today is actually going to be taking place in the 2-1 category of spans. What that means is that I'll only be considering 2 isomorphisms. So the cases where this morphism from F to G is an isomorphism in the original category C. So if you like, you can just think about those rather than thinking about 2 categories more generally. Okay, so let me clear these annotations. And we're off. Okay. So it's also worth pointing out that while the construction can't proceed by just listing off these 4 types of data, this same construction also works for infinity categories. So if C is an infinity category with pullbacks in a terminal object, you can form an infinity category span C, where the object morphisms and 2-morphisms look more or less the same as what I just drew, but now you have additional coherence taking place hidden in the construction. And there are a number of different constructions of such an infinity category using different models in the literature. I won't be making reference to any of those specific models. I'm going to try and keep the story that I'm telling here in the 1 and 2 categorical realms, and then point to how it can be generalized to infinity categories. So we have these higher categories of spans, and briefly, before we move on to what I'm going to be doing with them, I'd like to say a brief word about why one would care about such things. So there are some motivating examples, which hopefully will make it clear why this span construction is of some interest. And the first is extremely basic. We can consider partial functions as living in span categories. So let's define a subcategory of spans in set, where the morphisms are spans where on the left-hand side, we have an injective map of sets, and on the right-hand side, we have an arbitrary map of sets. Now, because injective maps are stable under pullback, or under these fiber products, if you will, this means that this really does define a subcategory or a sub-2 category of spans, and we can interpret each of these spans as really being a partially defined function, as taking a set X, picking out a subset and defining a function on that subset. And so this relatively simple example fits fairly naturally into this framework that I just described. On the slightly more complicated end, there are some geometric motivations coming from topological field theory and symplectic geometry. So in topological field theory, one's basic object of study is cobordisms, manifolds with boundary that you view as being morphisms from one boundary to another. And such a cobordism can be viewed as a cospan. Now here by cospan, I just mean a span where the two defining legs are in the opposite category, are pointing the opposite direction. So for instance, if we take this two-dimensional cobordism going from two circles to one circle, we can see the whole cobordism as the topological space that is this surface, together with inclusions of topological spaces. On the left-hand side, we have an inclusion from this disjoint union of circles, and on the right-hand side, we have this inclusion from a circle. And you can view this as a cospan. Now, it's worth pointing out here that usually when one's talking about topological field theory, one actually wants a little more structure. So we need to decorate this cospan with collar neighborhoods or smooth structures, whatever else one might be interested in. But the underlying composition is still just the push out. So the composition of cospans, at least when we're thinking about just the topological spaces underlying it. So this is another example that might be considered motivating for this kind of construction. And then coming from symplectic geometry, we have a slightly more involved example that one can take as motivation. So if M and N are symplectic manifolds, a Lagrangian correspondence from M to N is just a Lagrangian submanifold of the product of M and N, where M is now considered as having the negative of its symplectic structure, the opposite symplectic structure. And we can compose these. So we compose them in a way somewhat similar to the composition of spans. We take L1 and L2, and we take their fiber product, so their composition as spans, and then we consider the image in M0 cross M2. Now, some of you might be thinking, okay, in this geometric setting, this doesn't always work, and you're right. We need some conditions, transversality to start with, to guarantee that we get a well-defined submanifold when we take this pullback. But this composition works in enough cases that it's interesting, and one still can form a category using formal chains of Lagrangian correspondences modulo composition. This is what's called the Verheim-Woodward construction. And so why do we care about Lagrangian correspondences? Well, work of Verheim and Woodward from 07 and 09 shows that the Fukaya category is functorial in these correspondences. That is, if you assign to a symplectic manifold its Fukaya category, you can assign a functor to a Lagrangian correspondence in such a way that this respects the composition of Lagrangian correspondences. And there's also a higher categorical, an infinity categorical version of this. I give a couple of citations here, Kalak in 2013 and Haugzang in 2018, who give a derived Stacky version of the same sort of Lagrangian category of correspondences. But now in the infinity categorical world, what you're working with is some sorts of shifted symplectic stacks. And what you get then is that the analog of a category of Lagrangian correspondences really is a subcategory of an infinity category of spans. There's not this strange modification to the composition needed. And then finally, one can also notice that both C, the original category, and its opposite live in spans in C. And so a lot of the things that we can say in spans in C will encapsulate examples coming from either C or its opposite. So I don't have a slide on this, but I'd also like to say there are various linearization procedures that one can apply to spans. So you can take a span and you can define a functor from span in C to some other category that pulls back along one of the morphisms in a span and pushes forward along another. And such formalisms then also allow you to change statements that you might make about higher categories of spans into statements about algebraic structures in other categories or other infinity categories. And so this is, say, a fourth motivation, the study of categorified algebra, that might lead one to these spans as a natural object of study. Okay, now that I've hopefully convinced you that these span categories are somewhat interesting, the goal for today's talk is to classify some algebraic structures in span categories. And there are four types of algebraic structures that I'm going to be talking about today. One I'll only very briefly mention, but the first is A-infinity algebras or pseudomonoids. And now I'm giving these terms because formally this is what we are studying. A-infinity algebras being coherently associative algebras in a higher category, and pseudomonoids being a specific definition that's convenient in two categories or bicategories. But if you like, you can really just think of these as associative algebras. And one fairly classic example is a monoidal category. A monoidal category is an A-infinity algebra in the category of categories, or the two category of categories, I should say. And that will give you some flavor of what this A-infinity is supposed to mean, in that in a monoidal category, you don't have associativity of the tensor product on the nose, at least not usually. You have associativity up to two isomorphisms, natural isomorphisms, that satisfy some additional coherence conditions like the MacLane pentagon. And then the second example of algebraic structures that I'll talk about are Calabi-Yau algebras. And these are the ones that I'm not going to say very much about. You can think of these as categorifications of symmetric Frobenius algebras. I'm then going to be talking about commutative algebras or commutative pseudomonoids. And this won't really come up in this talk, but for those of you who are concerned which type of commutativity I mean in higher categorical settings, I will be meaning E-infinity commutativity rather than some En commutativity. And then finally, I'll be talking about Frobenius algebras. And more technically, I'll be talking about Frobenius pseudomonoids, again, because I'll be talking in a two-categorical setting. But it should be sufficient to think about these as coherent categorifications of Frobenius algebras. And again, when we come to that point, I'll say a little bit more specifically about what I mean. So, are there any questions thus far before I get into the first of these algebraic structures? Okay. So the first two of these come from my thesis work, the classification results in 2019. And the second two are a paper from a couple of months ago that's joint with Ivan Contreras and Rajan Mehta. So let's start with the associative case, because that's the case on which everything else will be built. And so what data am I going to need for an associative or coherently associative algebra in span C? Well, the first thing that I'll need is an object that will carry the algebraic structure. So if you want to draw an analogy with the category of vector spaces, an algebra, an associative algebra, consists of a vector space with some additional structure. And then, because we're working higher categorically, I am going to define many multiplications. So an n-fold multiplication for every n, or every n greater than or equal to 2, that goes from n copies of this object that carries the algebraic structure to 1 copy. And you can think of this in the vector space example as a sort of unbiased version of the algebraic structure there, in that if you have an algebra, you can multiply any n tuple, so you can define one of these n-fold multiplications. And then we need a unit. So this unit is going to go from the monoidal unit of span C to x1. And this in vector spaces would be a map from the base field to the vector space carrying the algebra structure that just picks out the multiplicative unit of the algebraic structure. And now, if you look at these data, and particularly at the somewhat suggestive notation that I've given them, you might start to suspect that these form a specific type of structure already. Namely, this starts to look a little bit like a simplicial object in C, right? We have an x sub I for every I from 0 on up, and we have some morphisms between it. So for instance, this x naught to x1 looks a little bit like the degeneracy map, the unique degeneracy map. These maps from xn to copies of x1 look perhaps like spine maps, and it turns out that those are exactly what they will end up being. And so already just from the data without the conditions, we start getting a sense of what this might happen to be. So let's keep that data off to the side and now start thinking about the conditions that we need for associativity. So associativity in this A infinity setting, well, if we were in the strict setting, we'd want to say that the n-fold multiplication composed with a k-fold multiplication gives us an n plus k minus 1-fold multiplication. And now, since we're in the A infinity setting, we're going to want to replace those with isomorphisms rather than equalities, but the same basic principle applies. So let's just try to write out what that looks like in span. We have our k-fold multiplication, and we plug it in to our n-fold multiplication. And we want to compose these and get the n plus k minus 1-fold multiplication. And so what that's telling us is there has to be a pullback square of this form, where x n plus k minus 1 maps down to xk and xn, which both map down to x1, and this has to be a commutative square and a pullback square. So higher associativity ends up requiring that certain diagrams be pullback. And if you parse this out, really try to work out what the morphisms in the simplex category are, you end up getting a diagram like this. And don't worry too much about the notation. It's not going to come up much. If you're curious about it at the end, we can go back and I can discuss a little bit more what precisely these conditions mean. But so we require these diagrams to be pullback. And as it so happens, the conditions that show up here already had a name in the literature and already had shown up when studying associativity of various forms. So Dyckerhoff, Kapranov, and independently Galvez, Koch, and Tonks defined precisely these conditions and called a simplicial object that satisfied these conditions, well, Dyckerhoff and Kapranov called these the two Siegel conditions and called these two Siegel simplicial objects. And Galvez, Koch, and Tonks called these decomposition spaces. I'm going to be following the convention, the terminological and notational conventions of Dyckerhoff and Kapranov throughout this talk. And so we'll call this a two Siegel simplicial object. So we have our data, we have our associativity condition, which gives us this two Siegel simplicial object, and then we have the unitality condition. And so this I'm not going to write out in the same amount of detail that I did before, but this also requires pullback squares that say if you plug the unit into an m-fold multiplication, you get the m minus 1-fold multiplication. So again, you get some pullback squares. And these conditions are what Dyckerhoff and Kapranov called the unitality conditions, not entirely surprisingly, but it turns out that these are implied by the two Siegel conditions. This is a brief note from a year or two ago by Garner, Feller, and Koch, I think. There are others. I'm sorry, I don't remember the full citation. Uh, but the two Siegel conditions actually imply the unitality conditions. And so in this context, we might expect an associative or a coherently associative algebra in spans to be a simplicial object satisfying these two Siegel conditions. And the first classification result that I want to share is precisely this. And in its full, gory, infinity categorical generality, this says that if C is an infinity category with enough limits, then there's an equivalence of infinity groupoids between two Siegel simplicial objects in C and A infinity algebras in spans in C. And so this says that this sort of intuitive picture I've just sketched really does exhaust all of these algebraic structures. So these simplicial objects really do exhaust all of the possible A infinity algebras and vice versa. It's also worth saying I glossed over a little bit of detail in that I claimed that the data here determine a simplicial object on their own, or I suggested it, implied it. That's not actually true. To get some of the structure maps of the simplicial object, you actually need these pullback conditions. That's how they arise. And so I've mixed and matched a little bit where things come in. But the intuitive picture really is what's going on under the hood. You have these data that give you the spaces or the objects involved in your simplicial object, and then you have these pullback conditions that arise from associativity and unitality. So, are there any questions before I move on? Okay, seeing none. The next thing that we want to do is add structure. So all of these other algebraic structures I mentioned can be viewed as an associative algebra plus additional structure and conditions. And so the general principle or the slogan that we're going to follow is that if we're adding structure on the algebra side, so adding structure to our algebras in span C and adding conditions, then we're adding structure to the indexing category on the two Siegel side. So if we add properties or structures to the algebra in spans, then what we're really doing is we're not changing the two Siegel conditions, these conditions that govern associativity. We're extending the simplicial object to a bigger or more complicated indexing category. And I'll say in a moment a couple of examples of what I mean by this, and then I'll go through two very carefully. So what indexing categories correspond to what? Well, Calabi-Yau algebras correspond to Kahn's cyclic category. And this is, again, the only time in the rest of the talk I'm going to really mention this example. But this is, again, work from my thesis. And this also relates to classification of topological field theories in that Calabi-Yau algebras classify certain higher categorical open two-dimensional topological field theories. And then commutative algebras, again, in this E-infinity sense that I mentioned, correspond to finite pointed sets. So instead of having a simplicial set, you have a functor from finite pointed sets to sets. And finally, Frobenius algebras are going to correspond to the paracyclic category. And both of these results are, again, from that recent work with Raj and Ivan that I mentioned earlier. And those are the two that I want to unwind in the remaining time available to me. And I should also say the proof in the paper most recently posted is just for the case C equals set. However, I am quite certain these results do hold in full higher categorical generality. And if somebody is interested in using them in that setting, I'd be happy to discuss how they might be shown in that setting. So the commutative case, again, restricting to C equals set. Well, here I'm not going to talk too much about what I mean by a commutative algebra. Hopefully, you all have some notion of what roughly that should be. And if you're confused about what the coherence should be, well, in a two category, again, you can think of the motivating example of a symmetric monoidal category as being a commutative algebra in the two category of categories. So how are we going to extend from simplicial objects to finite pointed set objects? Well, there's this functor that I'm calling cut following Lurie's higher algebra that goes from the opposite of the simplex category to finite pointed sets. And how does this functor work? Well, if we take some morphism in delta, so a map between ordered sets that is weakly monotone, that weakly preserves the order, then for each of these sets, I can take the interstices, the cuts between any pair of consecutive elements, and assign the base point to both the top and bottom. So these sort of outer interstices, if you like. And then, to get a map going in the other direction of finite pointed sets, I just draw arrows going the other way so that they don't intersect any of the arrows representing my original morphism. So here we see that 1 goes to the base point always goes to the base point, 2 and 3 go to 1, and 4 goes to 4. And so this formalism gives a functor from delta op to finite pointed sets. And now a generators and relations presentation of finite pointed sets shows that a functor from finite pointed sets to set is really just the data of a simplicial object with some additional structure satisfying some conditions. So it consists of the underlying simplicial set, where you have X composed with cut, which is just a simplicial set, and symmetric group actions, sigma n actions on Xn, because, of course, the automorphisms of the finite pointed set with n non-base point elements is just the permutation group on n letters. And then some compatibilities between these two structures, so some conditions. I'm not going to write all of those out, but you can find them in my paper with Viraj and Ivan. So we're going to then call a functor from finite pointed sets to sets to Siegel if the underlying simplicial set, this restriction to delta op, is to Siegel. So exactly the same pullback conditions we mentioned before, just now some additional structure on the indexing category. And so what kind of structure are we going to get out of such a thing? Well, if we start with a 2 Siegel functor from finite pointed sets to sets, we'll get, for example, this permutation isomorphism from x2 to x2. And what is this going to do to the face maps that define our multiplication? Well, the multiplication, the twofold multiplication, it turns out is defined by the pair d2, d0, the second face and the zeroth face. And this sigma, conveniently, just swaps those two. And so what this tells us is that this sigma gives us an isomorphism relating the multiplication to the multiplication with the inputs swapped. And now, obviously, this isn't a proof, but this is paradigmatic of the general structure that one gets as one examines these functors, these 2 Siegel functors from finite pointed sets to sets. And so these play, for instance, the same role as the braidings in a symmetric monoidal category, these sigma isomorphisms. So hopefully it is at least convincing that this should give you something like a commutative or coherently commutative algebra in spans. And this is precisely what we get. So we have the following theorem. There is an equivalence between commutative pseudomonoids in spans of sets and two Siegel functors from finite pointed sets to sets. It's worth noting that such functors are sometimes called gamma sets, where gamma is a category defined by Siegel that is dual to finite pointed sets, so that such a functor can be viewed as a functor from gamma op to sets. Okay, so then the final case that I want to discuss today is the Frobenius case. So this is where C is equal to sets. Again, we're still sticking in that framework, but again, all of this should generalize to higher settings modulo appropriate definitions and the level of technicality of the proof. So the first thing that I should say is, what do I mean by a Frobenius pseudomonoid? In the associative and commutative examples, there is some intuition to draw on. Monoidal and symmetric monoidal categories, for example, provide good intuitive examples where you can gain some intuition. But here, I should at least sketch what I mean by a Frobenius pseudomonoid. So it's going to consist of an A infinity algebra or an A infinity monoid, which I'm writing as shorthand. The object that carries the pseudomonoid structure, the n-fold multiplications, and the unit. And I'm going to draw these diagrammatically as string diagrams. And I should warn you here that unlike some places in the literature, I read my string diagrams from top to bottom, and that's how these pictures should be interpreted. So for instance, the threefold multiplication, we can draw as a tree with a single root and three leaves. And the unit will draw as a tree with a root, but no leaves, a little circle instead of leaves. And the conditions that this be an A infinity algebra look something like this. So if we plug an n-fold multiplication into an n-fold multiplication, well, now there is an isomorphism from this composition to the n plus m minus one-fold multiplication. And there's also this isomorphism when we plug in the unit to, say, our threefold multiplication, and that has an isomorphism to the twofold multiplication. And then these isomorphisms have to satisfy some coherence conditions. So then the additional data in the Frobenius case is we need a counit. So a morphism that goes from x1 to the monoidal unit. And I'm going to call this eta, and I'll denote it by something that just looks formally dual to the unit. It looks like a unit upside down. And then we need conditions. And these conditions will be familiar, for instance, from topological field theory, if you've looked at two-dimensional topological field theory. But for example, they will be things like you have an isomorphism, a two-isomorphism, from this composite of multiplications, identities, unit and co-unit, to the identity. And so this is a sort of non-degeneracy condition, if you want, a categorified non-degeneracy condition. So then I claimed earlier that the corresponding indexing category is the paracyclic category, but since this isn't a particularly familiar category, I want to provide two perspectives on how one can view lambda infinity, the paracyclic category. So the first is topological. You view the objects as oriented circles with some non-empty collection of marked points in them, and equipped with a universal cover together with the pre-images of all of these marked points. And then the morphisms are orientation preserving degree 1 maps of marked circles together with a lift of that map to the universal cover. And all of these maps have to preserve the marked points. So send marked points into marked points. Technically, one has to take homotopy classes of such maps of spaces. Rel the marked points, of course. But this yields a category that's called the paracyclic category. However, this category also has a more algebraic presentation. We can say the objects are the formal symbols n for n greater than or equal to 0. And the morphisms, well, a morphism from n to m is a map from z to z that satisfies this periodicity condition, namely that f of k plus n plus 1 is equal to f of k plus m plus 1. And we can then see that the simplex category can be viewed as a subcategory here, just by considering the simplex category to consist of those morphisms that send the interval from 0 to n to the interval, 0 to m plus 1 to, no, 0 to m to 0 to n. And similarly, from both of these perspectives, we can see that the automorphism group of any object is going to be a copy of Z. Okay, so this is the paracyclic category. And now, in the same way as we did for finite pointed sets, let me break down what a paracyclic object consists of in terms of maybe some more familiar data. So the data are going to be, well, the underlying simplicial set. As I said, the simplex category is a subcategory of lambda infinity. And so such a functor has an underlying simplicial set. It's going to have automorphisms, tau from xn to xn for each n greater than or equal to 0. And these will generate those automorphism groups, those Z automorphism groups that I mentioned before. And again, there will be some conditions, which I'm not going to spell out, but that effectively add some commutation relations with these taus to the simplicial identities. So once again, we say that a paracyclic object is 2 Siegel if the underlying simplicial object is 2 Siegel. So same pattern as before. And from such a paracyclic 2 Siegel set, we get this morphism eta, which is just going from x1 to the terminal object. And instead of taking S naught, instead of taking the unique degeneracy, we're taking the unique degeneracy composed with tau. And so we get this co-unit, and it's then a matter of some algebra to check that this gives Frobenius pseudomonoids. So the final theorem that I wanted to state is that given this construction, we have, again, the same sort of equivalence between Frobenius pseudomonoids in spans of sets and 2 Siegel paracyclic objects in sets. It's worth commenting at this point, the case that I omitted, the cyclic category, can be viewed as something like a quotient of the paracyclic category by some additional relations. And this mirrors the way in which symmetric Frobenius algebras are Frobenius algebras satisfying some additional conditions. In this case, we see that the Calabi-Yau pseudomonoids are Frobenius pseudomonoids satisfying some additional conditions. And so the relationships between these algebraic structures categorify quite nicely in this setting. Okay, I seem to have rushed a little bit when I ran this last night for time. It came in at 55 minutes, but that's all I wanted to say. So thank you very much for your attention. And if you have any questions, please feel free to
We
ask.
thank you very much. So actually, any questions or comments? Maybe I will start asking some questions. So the A infinity uh, uh, categories that you described are like the categorified version of associative algebras, right? That you said.
Sorry, give me
Oh,
one moment. Uh, you're a little bit garbled. Give
huh.
me a
Uh,
sec. It might be. Sorry, one moment. I am going to try reconnecting my headphones.
yeah. So these are like the categorified versions of associative algebras, right?
Okay,
Uh,
is this any?
can you hear
Perfect.
me? Wait.
Yes.
Huh? Can you hear me?
There's,
Yeah.
yeah.
So these are modeled on associative algebras, right? These A infinity categories and so on.
Well, so A infinity algebras are, you can think of as the coherent avatar of associativity. So one way of thinking about this is if you think about it classical homotopy theoretically, you can say you take a cofibrant resolution of the associative operator.
Right. So the reason I ask is that there is a very rich classical theory of associative algebras. For example, one can consider central simple algebras and
Hmm.
Brouwer groups classifying central simple algebras and so on. Are there
Hmm.
any counterpart of these things in even quaternion algebras are like very important? Like, are there
This is a
any? Yeah,
this is a good question, to which the answer is not to my knowledge. So we have thought about trying to extend, for instance, things like the special Frobenius condition to this setting, and so we've looked into a little bit some of these other categorifications, um, and I'm not aware of a canonical version of the, say, infinity categorical version of any of the constructions you just mentioned. That
I see.
said, it is something that we would be somewhat interested in, is giving diagrammatic higher categorical presentations for some of these constructions. Again, our long-term aim is to apply these classifications to study topological field theories valued in variance of the symplectic category.
The result that you will obtain eventually will be like generalization of, we know that category of Frobenius algebras are equivalent to uh, two-dimensional TQFT, right? Category of,
You need commutative Frobenius algebras in that
right,
case,
right.
because you have this E2 symmetry in some sense in the two-dimensional. So yes, that is part of the motivation here. However, this is also a little bit tricky because classifications of the, or presentations of the infinity one category of two-dimensional cobordisms don't really exist. So you don't have that same classification result right at your fingertips. You need some work. Um, but there are a number of state sum formalisms that we're also hoping to be able to adapt to higher categorical settings.
I see. Yeah. Thank you. Any questions or comments?
Uh, I was going to ask about that TQFT question. So, uh, in there is something called non-commutative topology, and they study non-commutative C-star algebras. So, is there something, for example, I mean, is there a way of non-commutative version of, I mean, can we look at this as a non-commutative version of that TQFTs, 2D TQFTs at least, or
Mm, not to my knowledge,
is there, I
no.
mean, is it studied under this title or something?
Non-commutative,
Okay.
not really, no. So sorry, maybe I misheard. You said non-commutative TQFT?
Yeah, I mean, Frobenius algebras and commutative TQF, I mean, sorry, commutative Frobenius algebras and TQFTs are equivalent.
Yes,
So
yeah.
just like the, I mean, there was like similar equivalence between Gelfand duality between.
Okay.
So they just sort of abuse the duality and say that we are studying non-commutative spaces while studying non-commutative sister algebras. So is there are
Interesting.
there
So
similar approaches to
I am not
a
aware
lot
of
of
any, and it's not something I had thought about, but it would be something I'd be interested in discussing further at some point.
yeah,
Yeah,
there's a lot of K theory stuff going on there.
yeah.
Algebraic K theory.
Actually, there is even something called
Transformers.
non-commutative topos. I mean, based on non-commutative topology.
Oh,
Well,
up to date study.
that I think does live in a somewhat different realm than this. So I should say the TQFTs that we're most interested in working with are in some sense very classical or standard cohortism categories, just valued in slightly more exotic targets.
Any more questions or comments? So, okay, let's thank our speaker once more. Thank you, Volker. It was a really nice talk. I mean, we all enjoyed very much. We will meet
Very glad
2
to hear.
weeks, yeah, 2 weeks later, and hope to see all of you again. Bye bye.